In the previous two videos, I gave you some revision on functions. So now it's enough revision. We're going to try and crack on with trying to understand the derivative of an inverse of a function. So when you're given a function, let's say this one here, if you get a graph plotter, it will give you this red line here. Now the inverse function, which is this blue line here, will always be the reflection along the y equals x line here. Okay, it's always a reflection. Now, if you try and understand the gradient of this line here of our original function, let's look at the point 0, 2. So 0, 2 is this point here. If you look at this gradient here, the gradient is the up and down here is 3, and the across here is 1. So the gradient is 3 over 1. Now, looking at this point here, at the moment it's 0, 2. So the inverse will be 2, 0. So that's this point here. So it gets reflected to here. Now, if you look at this point here, it would be 1, 5. That's this point here. But then the inverse function will be well, at the moment it's 1, 5. The inverse will be 5, 1, which is this point here. The thing is, the gradient of this line is 3 over 1. And then if you look at the gradient of the inverse, it's 1 over 3. And as it turns out that if you can work out the gradient of the normal function, the gradient of the inverse function will always be the reciprocal of the normal function. So the gradient here is 3 over 1. The gradient of this line here will be 1 over 3, because when you make the reflection preserves everything. It doesn't get squeezed or stretched. It preserves everything. So a reflection will preserve this length, which is 3 here. A reflection will preserve this length here, which is 1 here. It's not like a stretch or a squeeze where you would change. Well, a reflection will always preserve the length. So even if you have a different line, let's look at this one here. Okay, even if you have this line here, if you look at the point 1, 3, so the gradient here, let's look at this gradient here. Hang on, let's look at this triangle here. Okay, so this point here, so the height here will be 5. Okay, the height here will be 5. The across here will be 1. So the gradient here is 5. Okay, but let's look at these 2 points here. Hang on, let's look at this point here and this point here. Now this point here, currently it's 1, 3. So the inverse point will be 3, 1, which is this point here. So this point gets moved to here. Okay, now this point here, currently it's 0, minus 2. So the inverse will be minus 2, 1, which is this point here. So this point here gets moved to here. Or yeah. So now if you now look at the gradient of the inverse function, it will be the height here will be 1, the across here would be 5. So the blue line here, the gradient for the blue line here, remember it's 5, 1. 5 over 1. So the gradient for the blue line here is 5 over 1. Now the gradient of the red line will be 1, 5. 1 over 5. So you can see here the gradient for the blue line is this. The gradient for the red line is this. So again, it's a reciprocal. And you can see why it's a reciprocal, because when you make the reflection, it preserves, well, this is 5 here, 5 here. And then the 1 here, well, it gets, well, yeah, the gradient's always the reciprocal. Okay, even if it's a curve. Wait there. Hang on. Even if it's a curve. So this function here is f of x equals x squared plus 1. Okay, so if let's say you look at this point here, 1, 2 here, and 2, 5 here. Let's just pretend that the gradient here is 3 here. 1, 2, 3. The height is 3. The length here is 1. So let's just pretend the gradient here is 3 over 1. Well, when you make the reflection, this point here, this point here, well, at the moment is 1, 1, 2, so the inverse will be 2, 1, which is this point here. So again, you can see that this point jumps to here. Okay, if you look at this point here, it's 2, 5. So this point here will be 5, 2, 5, 2. So this point here gets moved over here. You can see again the height here is 1, the across here is 3. The point that I'm trying to make is that if you can work out the gradient of this point here, then when you look at the reflection at this point here, then you can also find you will automatically know the gradient at this point here. If you know the gradient here for the red line here, then if you want to know the gradient of the inverse, then just take the reciprocal of the gradient of the red line, and then that will, you can find out the gradient of the inverse without having to work out the inverse. So for example, let me give you an example. So here, let's say you've got a function here, f of x equals x to the power of 3 minus 2. The question is, what is the gradient at what is the gradient of the inverse function at x equals 6? Okay, so rather than rearranging this, rather than working out the inverse function, okay, rather than working out the inverse function, you can just find out the derivative of this function and then take the reciprocal to work out the gradient of this of the inverse function. So hang on. So originally the question was, given this function here, find the gradient of the inverse function, which is the blue line here, at x equals 6. So at x, so basically the question is saying find the gradient at this point here. Okay, so normally, well, rather than having to rearrange this to work out the inverse function and then differentiate the inverse function, you can just work out the gradient of this function and then take the reciprocal. That will automatically give you the gradient at this point. So hang on. So originally you were given this function here. So you can imagine this as being like a machine. If you put 2 into here, you will get a 6 out. Okay, so looking at this here, this is 6 here. So you want to know the gradient at this point. But you looking at this here, if you put 2 into here, then you get a 6 out. So the point is that when you put in the 2, that's this point here. Hang on, 2. So you see, to work out this point here, you will need to work out the gradient at this point here. Okay, this is the hard part. You got to identify what point on the original function you need to work out in order to work out at x equals 6. So here, if you sit down and think about this, if you put 2 into here, it will give you a 6. So to work out at 6, to work out at x equals 6 here, you will need to work out the gradient at this point here. So the gradient is really at x equals 2 of our original function. Okay, so we need to find out the gradient at this point here. So differentiate this. So given f of x equals this here, f prime of x equals let's see 3x squared. That's it, 3x squared. Okay, so now we want to know the gradient at this point. So we would need to put this into here. So we need to put the 2 into here. Basically, in short, you need to figure out a way of finding out the gradient at x equals 2. So put 2 into here. That would be, this here will be 4. 4 times this would be 12. So the gradient at this point here is 12. Okay, the gradient here is 12. So the gradient over here, well, 12 is like 12 over 1. So the gradient at this point here will be the reciprocal of this, which will be 1 over 12. So the gradient at this point here is 1 over 12. You see, from here we can pretty much jump to the gradient here, rather than having to work out the equation for the inverse function and then differentiate the inverse. It takes a long time. So just differentiate, well, blah blah blah. Okay, so so that's how you do it.